Yeah, just a second. There you go. Oops. Did you see Fernando, the original Toy Story? Pixar. They had this saying to infinity and beyond. So that was Buzz Lightyear's big spaceman toys. Infinity and beyond. So exoskeleton. So your title, your title made me think of
Buzz Lightyear.
Buzz Lightyear.
So I'm turning on the microphone.
I think, does that sound right? That was the say. Pretty sure that's right. We are.
Must be sitting here, must be feeling like a PhD defense. I feel like we're not gonna fight.
Actually, it's 9. So welcome to the last day of the HPC LAMMPS master class workshop. Thank you, Axel, for putting this together. Thank you to all the activities and the people who's connected, I hope, for the YouTube stream. So, my name is Fernando Posada. Right now, I'm an HPC engineer at the Oak Ridge National Laboratory Leadership Computing Facility, also known as OLCF. And I have today the privilege to talk about our experience as a center in running molecular dynamics, specifically LAMMPS benchmarks in today's fastest supercomputer, according to the top 500 exascale computer frontier. And in particular, when I'm talking about this, it was titled Pushing Classical MD to Exascale ND. Big shout out to Nick Hardy, my colleague, who helped me to basically put together the presentation and get me the privilege to basically talk about mainly his work. Okay, so let's dive into the matter. So this is HPC at the OLCF. So since it was in the 2004 founded, Oak Ridge National Laboratory has had at least one supercomputer in the top 10, top 500 list. But we are going back in time to 2010 when we had the first one, the world's fastest supercomputer in 2009 was Jaguar. It has a theoretical peak performance of 2.3 petaflops. That was a multi-core CPU. Then in 2012, we moved to the hybrid architecture. So we had the GPU-CPU architecture with a peak performance of 27 petaflops. That was Titan. Then we had in 2017, actually was registered in the top 500 in 2018. Also, the world's fastest computer at this time was a hybrid pulse GPU CPU with a theoretical peak performance of 200 petaflops. Still today in the top 10, right now it's the number 9 in the last edition, and it's gonna be decommissioned soon, but still active. And we have now Frontier, which had the test in 2022, but it was deployed in 2021. And it has a peak performance of 2 exaflops. Right now it's running at 1.3, if I'm not incorrect, in the top 500. And this presentation is going to be focused in Frontier mainly, but we also have some tests in samples. So let's dive a little bit more into our 2 active machines. So 2018 Summit, it has 4,680 nodes. It's a IBM Power 9 machine, has 6 NVIDIA GPUs B100 per node. As I already mentioned, it has a 200 petaflops theoretical peak performance. Right now it's the number 9 in the top 500. It has an InfiniBand network with a fast 3 to 4G. On the other hand, we have Frontier. It has almost double the number of nodes, 9,408. The CPUs are AMD EPYC, then it has 4 GPUs, AMD as well, MI250X. Even though there are only 4 GPUs per node, each GPU has 2 what they call graphics compute dies, so they can count as 8 GPUs each node. It has a theoretical peak performance of 2 exaflops, but it's not running at 2, it's running 1.3 or something like that. Currently, it's the number 1 in the top 500, and it has a Slingshot 11 network with a Dragonfly topology. That's it. So basically, this is what I'm going to talk today about. First, I'm going to explain what is the OLCF vision in regards to why are our benchmarks they were they are. Then I'm going to talk about the OLCF 6 benchmarks. Remember, Frontier is the OLCF 5 machine. So we are going to talk about the next machine. What is next after Frontier? Then the strategies that we use to scale both in Frontier, then additional improvements, thanks to our communication, NPI communication study. What were the key challenges, some recommendations for people that are listening to us, and do the conclusion. So let's dive into the OLCF benchmarks and why our benchmarks the way they are. So basically, we are focused on weak scaling benchmarks, and this is very important. So for those who don't know what a weak scaling is, so you have 2 types of scaling. You can have a strong scaling, which is the most famous, I guess, in which you have the size of the system fixed, and then you scale it up to a number of processors. So you will change the number of processors that you have. Ideally, a linear scale if your application scales well. But weak scaling here is important because we are interested in pushing the size of the system to the limit of the machine. So in this picture here, you have different sizes in meters for the systems. And you see as they grow in size, the computational resources needed for them to run also increase. So I have here some examples like HIV, influenza, SARS-CoV. So the number of petaflops needed to run those simulations also increased. Right now, we would like to be on the ECOBAF. So these benchmarks you are going to see, we're about to see, they are right a little bit in the right mouse, right here in the micrometer area right now. I think it's important to stress that this simulation is probably the biggest one with long-range interactions made in history. Okay, so let's go to the benchmarks. So we have 2 different types of benchmarks. So they are featuring short and long-range interactions for molecular dynamics. The first one is the React effect for the what's it called? 20-erythritol tetranitrate crystal. And that one is for the short range interactions. So we use the potential reactive PEP. The time step in femtoseconds was 0.1, only 100 steps. The thermostat use was MBE. The number of atoms for the reference system was in total 200.49 billion of atoms, which makes a unit cell length of 1.4 micrometers. And in the other hand, we have the long range, which are SPCE bulk wire, it's a liquid wire model, that uses those potentials, and in particularly noting that it's using P3N. So it actually already poses a very huge challenge for computation at scale, as you will see later. And in total, we have 0.5 femtoseconds for a total of, 100 steps as well. And the number of atoms that were modeled in the reference system, so at full scale, is 466.12 billion of atoms for a unit cell of 1.7 micrometers as well. You might actually be asking why this number of atoms. So they are absolutely tied to the size or the capacity of the system. So in the benchmark, they provided different sizes of the benchmark with different replicate commands. So for those who know LAMMPS, they know what replicate means. This is a cubic one. So if you see 72, for example, in the first one, that would be 72, 72, 72 each axis in a cubic way. And that would be basically the scaling logarithmic cubic with respect to the number of nodes because of the capability of the machine. So as you can see, scaling, we are increasing the size of the system to keep constant the load for each node. That's more or less the idea, while increasing also the number of nodes. So that's why the size increases, while at the same time you increase the number of nodes. Okay, so this was just additional information. Important to note, actually, I forgot, you can find the benchmarks online right now if you want to go olcf.ornl.gov / if you cannot see the thank you benchmarks, or you can scan the QR right there and you can get there quite quickly. If you want to follow the talk also by looking more detail, because in there you can have actually the whole files, including the input files, output files, and details, rules, how to run this benchmark, and what are things that you can do and not, if you wanted at some point to run them on your own. Okay, so the results. So for the React FF, there was basically nothing to be done. It was a very excellent, we got excellent weak scaling, about 78% at 9,261 nodes. Because basically React FF doesn't suffer from a communication bottleneck. So because it only has short interactions, so it will be communicating to only neighbor processes. So there was nothing else to be done in that side. The only or the primary bottleneck was the memory bandwidth and a little bit of the float 64 vector compute. But besides that, I think the scaling was absolutely pretty good. There was nothing to be done with the code in that regard.
Can I ask a question?
Yes.
So do you happen to know what fraction of the time the QEQ charge equilibration took, and did that percentage grow as the size of the problem grew?
I do not have the data here, but we can, because we have the outputs.
Okay. Yeah, that'd be really interesting to look at that breakdown.
Because QEQ is basically solving a sparse matrix problem, but in terms of its scalability, it's thought that it's going to kind of degrade a little bit the larger the system gets. But if you're replicating a regular system, it could be that it's easier for that system to actually solve the QEQ equation, because really QEQ needs long range information to equilibrate charge across the entire system.
Right.
So for a heterogeneous system that size, QEQ might perform worse as well. And it would perform worse in the sense that it just takes more iterations to get a converged answer.
Okay. So actually, this is atom steps per second, million atoms per second, basically, unitary there for the number of nodes. So it's only looking at the time steps more or less.
Yeah, but each time step it has to do this.
And I have to
QEQ.
say now that saying what you mentioned.
Yeah.
I'm not an expert in molecular dynamics. But all of this that is being recorded, thankfully, is going to be very useful for us to look into the details of the benchmark. Okay. So I appreciate it, and feel free to jump in and do any, I don't know, comment that might actually clarify things for you.
Yeah.
Thank you.
I would expect the Q key converge slower with more matrix elements, just because of the floating point noise that you pick up.
Yeah.
Which are converging to finite precision, and the bigger the matrix, the more noise you pick up.
So this issue of QEQ scalability for really large systems is something Stan and Aiden, our colleague at Sandia, know about, and they talk to other people who React experts. And so this is within the field of Reacts. This is an interesting question.
Right. It's good to know. And very quickly switching to the other one, which was more challenging and probably interested for this talk, is the SPC model with the water, liquid water, room temperature, I think it is the one. So we have issues. So that plot was actually the result, even though there was very poor weak scaling, only 40%, and 9,261 nodes to the reference amount of nodes. There was a lot of challenges to be able to put together this graph. We were limited at 64 nodes. That bad with nodes. But in general, after we came up with some fixes that you will see later, and actually shout out to all the people in this room, basically 50% of the people in this room who are LAMMPS developers who actually helped us to track down those issues very quickly and to fix them. But here, we want to feature this issue that we have at 512 nodes. There was a FFT load balancing switch that triggered at some point and basically degraded the scale at this point. After the switch, you can see the scaling gets better up to that point, something happens. I think is one. Is up to where the scaling could be somehow, right? So we'll see some details in that later. Okay.
Is this single or double precision FFTs?
I think they are both.
Yeah. And that's on the CPU or with the GPU?
GPU.
Okay. Yeah, then you can change it.
So you're saying that before these changes, bug fixes, whatever, that blue line was worse than it does in this plot? The scaling wasn't as good as
So
it
this-
is now?
So before the fixes,
Yeah.
the line only got up to 64. So that will be here.
Because we have an integer over.
So that's
Oh,
the
this is
next
such a
slide.
huge problem per
Yeah.
processor.
So we were able to be able to get this graph, even though the scale was not great after many fixes. But right now, even though there are some fixes as well for this load balancing.
Yeah.
The results were not updated. So I think right now it's looking even better. And maybe it's to make it look better.
Okay, but you're saying where you do the circle there at 512,
Because we want
there was there's something automatic that
yeah, that
happens in the
switch.
LAMMPS FFT
There was a load balancing strategy, I guess, for FFT.
Yeah,
That was implemented in LAMMPS that was actually turning on.
Yep.
At that point, and then it was getting degraded performance. Of the solution.
so the load balancer hurt the performance.
Yes, exactly.
So now you ran this with disabling that or turning it off or something, so now
Yes.
now it's the better.
We had
one?
to, I think.
There's a pending pull request.
Yeah.
There is a pending pull request for it.
Okay.
Yeah. So basically, at the reference scale, 50% of the time was basically spent on the key space using NGI sense. And that's why there is an additional communication style here in the presentation. Maybe we can propose some improvements. Actually, you can give us some insight whether they are possible. Some of them are not implemented, they're just we wrote them here, so we can have their input.
Yeah, so I think at that scale, the next step we have to look into is port value splits to Cocos so that you can run the K-space on a separate set of nodes.
Exactly, that's also another, we get there, okay, patience. Okay, so before getting into the details of how actually get the results, that's a huge part of the presentation. So I have to say an auto validation. So historically, GPU based benchmark like this one are validated by CPU based version. However, we didn't run them in the CPU because it will require the whole day, very large amount of time for running this simulation only in the CPU. But we still provide the capability, so we can actually try to do it. People who wants to run, but as a benchmarker, let's say, we didn't. Instead of that, we have scientifically validated quantities of interest. So, for example, for react effect, we examined the energy per unit volume of every 10 steps. They just must be kind of constant, doesn't change too much. And for the other one, SPCE, so we have the potential energy per molecule that must be within 11.12 kilocalories per mole per molecule with an error of 0.02 kilocalories per mole. That is more or less the quantities that are required to validate the results for anybody presenting those benchmarks. So now let's go to the part everybody is interested in hearing is basically how we actually got these results. So as I already mentioned, first things first, the React setup needed very little help to scale. So of course, just working out of the box. But then for the other one, we have to then fix several issues. So we have the pull request 4037. And this one was to fix the integer overflow in P2M and the read communications, what they call the DOP, so degrees freedom, correct. Those access doing, thank you. And then we had 4047, which basically had a fixing a bug in Cocos fix shape command. And there was another unpack changes fixes there. So that one got us to the plot that basically I show you. There was some code improvements as well. So it was the pull request 4007. Basically, we coupled Cocos and non-Cocos FFTs at component runtime. Was something to make the benchmark more general. So you could say use non-Cocos or Cocos for FFTs.
So I'm not clear what decouple is.
The issue was you couldn't directly select the hip FFT. Because if you had GPU, it would go to CUDA
Oh, yeah.
FFT. There was just previous, I mean, that hadn't been that anything was running Cocos on him significantly before, and so it wasn't done. And when Cocos FFT was integrated in the build process, it was done with the minimum set of changes, so it doesn't give you the maximum flexibility. We had to change the names of the defines. Previously, the same defines were used for Cocos and for the CPU. And then you could have the different FFT in Cocos simply because on the CPU you don't use CUDA FFT. And now there is a select FFT for CPU. That's the old ones, and then there is FFT Cocos, and then the name of the FFT, so that you can separately pick any of the choices you have for Cocos that are independent from what you use on the CPU. Otherwise, you were forced to use either FFTW on the CPU or KISS FFT on the GPU, which is by far not as efficient as the HIP FFT.
Okay, so now it can use the native CUDA 1D FFT or the native HIP 1D
Yes.
FFT is what you're saying.
Yeah, this just really said that you could build a Cocos FFT library and a CPU FFT library, and they could be different. Previously, they'd be the same.
And then you can do this compound, which would be the compiler and add runtime.
Got it.
There was a performance improvement in the Coco sorting, which basically limited to the CPU, if I'm correct.
Just sorting of what?
Um,
Just the sorting thing we talked about?
Yeah, it was for the building the that.
The automatic.
Okay, gotcha.
And in progress, we have this key state modifies collective yes, which is basically to run instead of point-to-point, use collectives. I'm gonna talk about that later, so it's really in progress and but as everything you want to try, it might work or it might not. Yeah,
Yeah,
Kind
this
of
is
work.
like porting the stuff from Paul Kaufman from the blue sheet, right?
okay, so strategy is to run the bug free, so the already fixed, the one that gave us the plot that we're still improving. So basically, if you're using Slurm, these are recommendations for users. You should be using something called svcast. So svcast is a Slurm utility that basically puts any, not only for LAMMPS, but for any programs, it will put all the library binaries in the local nodes disks. In this case, they are MB, MIs, but it could be the local space, TMP or whatever. Because if you have running 9,000 nodes with so many processes, each one trying to get the libraries from the shared space, that's gonna take a long time. And it's gonna stress a lot the file system. So this is a technical detail. So it is important. So it will put everything locally, will copy the binaries from the shared storage to the local storage, and everything then will be run locally.
So is this something useful for running any code on full?
Any code.
Okay.
So I think it's encouraged for
It,
anybody.
it would
to
be
use-
for any bigger cluster
For
if you
any
have a
bigger
shared file system.
Yes. I would suggest you can do it. So you can actually save these runs are not very long, but you can actually save 5 minutes of the total runtime, just 5 minutes.
I think sometimes you'll get like timeouts too, right? And it won't even run.
Yes, because they are waiting for there is so many things trying to get to the shared storage. You might get
the
timeouts.
MPI init.
And remember, the storage is a lustre file system. So if that tells you something, so might actually have timeouts. Okay.
Well, yeah, you would have to configure the folder where you store all this stuff special so that it's more distributed.
Okay.
But it doesn't work for small files anyway, so if you dump it into a local storage, that would definitely be the preferred.
Yeah, so the storage is going to, it's going to impact it.
And the SPCast it goes to the temp folder, which is a RAM disk, which would.
You can put any location, but by default, you also have it. And if they are using the proper configuration of them, it might actually be a part of the project. No, actually that is. But this case is using them for frontier. Then the other optimization is that you have to ensure you have a 2x2x2 subgrid on each node 8 times. So one per each compute die, that will be each for each GPU. That is also helpful because it basically encourages the communication within the nodes. That improves performance a lot.
So is this with the processors?
Yes.
Nice.
Okay, yes, the processor really that things. And then when you are running GPU over MPI, you might have some slowdown, but it depends on the MPI implementation. So this is what I'm going to say later. And then you have to be very aware of the CPU GPU affinity. So you have to use some Slurm tweaks to be able to attach and basically to fix the affinity of the CPU and the GPU so they don't get messed, like different CPUs trying to access the same GPU. So that is very important for performance.
So 10x slowdown means you would go from like 50% efficient to 5% efficient if you didn't.
Yes, so if you don't do MPI over GPU, just only, for example, anything like it would be 10 times. So
Yeah, I mean, for the SBCE at large scale, your K-space is dominating the performance, and in K-space, the MPI performance is dominant at that scale.
So an explanation for this is here, a closer look to the actual node in Frontier. So you have on the blue squares, this is the processor. And each one of the processors. And then you have the GPUs, and this is very important. The reason why I'm showing this is basically that you have 4 GPUs, but each GPU has two graphics compute dies. So you can count them as 8 GPUs. Interestingly, the network interfaces or NICs are connected to the GPUs, right? And you have one per each GPU. Okay, so basically, 2 graphic dies are sharing one network interface. So everything that is communicated through the network is going to go through the GPU.
Even if you're doing CPU
Yes.
MPI calls.
Exactly. So in Frontier, particularly, you have to use NPI, GPU aware NPI. That's the reason.
Even if you're running on the CPU only code.
Yeah. So actually, I wanted to show a case of a synthetic benchmark as well, because you can tell it's not doing anything, any calculations in the GPU. So you might actually think I'm just testing, for example, I send, I receive, that's it. There is no operations. I'm just sending a message, receiving a message, and timing. If you don't do the heap implementation in this case, it will be slow, because then you will be moving data from the processor, not from the GPU. But if you allocate the data in the GPU and then do the I send receive, it will be much faster.
Cool. So is Frontier the first supercomputer to put the NICs on the GPUs directly?
But this is
I've never heard.
I never heard about it. But actually, when I was doing this benchmarking thing, I was thinking, I'm not using the GPU, so what is the point of doing that?
Yeah.
And everybody was telling me, yeah, you should do that, but why? I don't know. This is
So I wonder if Aurora did that.
It's very interesting, yeah. So this basically, the takeaway is that you have to know your computer architecture to be able to get performance, the maximum performance. Basically, that's it. And then moving forward, we have other strategies like I mentioned before. So the atom sorting of was moved to the CPU. So the GPU sorting was fixed then because it was not working. So we moved it to the CPU that was fixed. So it could be used. The only caveat at that is that the replicate dimensions must be lower than the int max, otherwise it's going to explode also the number of replicate. But you can use many replicates. That's the you can do different replicates.
Replicating stages.
Right.
Yeah. So what is the total number of replicates?
So it was in one of the slides before. Let me show you. So this will be the replicate one here, right? So if you multiply that big number of atoms, it's going to explode the integers, right?
Yeah.
So you have to do it in stages.
It's 3.4 billion.
Wow. So it is huge.
No, this is a
Oh,
React.
that was the React.
It's,
So the first one is the React, and
17.
the lower one is the wire.
Okay, now I got it.
So yeah, it is a huge number that is going to overflow the integers.
would there be a way to just use the big one on that, like a 64-bit integer?
Actually, the fixes for the integer overflow was basically to recast the integers for the degrees of freedom. But I don't know why exactly. Maybe Axel knows. Why in the replicate we have to still to be less than int max.
There's communication calls that use int, so it would be a mess to report it.
I mean, even if you want to do something oddball like like that, 1500 by 1500, you could just do 1500 in one dimension.
Yeah, that's what
1500
it
in
is.
two, exactly the number you want, third dimension. So
By step, so it will work.
Yeah,
So
it will work.
that's the only thing you have to be aware of.
I think that's a better way. to work.
Because of course, when you have integer overflows, the errors are going to be random, right? So very hard to track down.
We should check for it and protect against it. But
I think the fix to this one is that there is a protection there. So I actually put that warning.
Yeah, we have an if statement now, and
There
it
is no if
stops and says
statement.
that you should do multiple replicates.
Yeah, that was put in place, so to avoid that, reaching to that.
I will say, I don't think a lot of people are gonna find it.
And this is one thing that you already mentioned, and in the other bullet point, and it's that we didn't actually do the partitioning, so using a subset of processes to take care of the criteria computation. That is something that could be implemented, but we didn't do, and we were not interested at that point on doing so, because it's gonna, the idea of the benchmark is also to be general. So it is for the next system. I know it's running now, but nobody knows how it's that one. But to be considered at some point.
For these kind of systems, actually separating out the K space in a separate partition, it's done as an option in GROMACS. It's automatically done by NAMD because of how it parallelizes. So it's the natural thing to do actually for these things, because the K space stuff at some point just scales out and you can't force them to use more processors.
I will agree that for the sake of knowing what happens, it would be worth it.
So one thing that would be interesting is to plot their K-space time and see if it's actually, peaked and, or, if it's actually increasing or if it's still scaling, like at the
I have plots for multi-threading where it's very clear that the K-space time goes up almost exponentially.
Right.
Here it's so
But here-
big, it might not be
Yeah.
actually turning over, I don't know.
Yeah,
It's a good thing to plot.
we should just see if it's turning over. If it hasn't turned over yet, then it may not be worth it.
If it's not, it might not be worth it. Okay.
Well,
That is important.
I mean, one good thing is you're already using this little 2x2x2 grid to represent the 8 GPUs in one node. And that's exactly the position you need for delay split. And what you would do is dedicate one or two of the GPUs to the FFTs, and the other 6 or 7 would work on the non-D3M stuff. And then everything's still local because it's the data just needs to pass back and forth between those GPUs to, and within a node to exchange the information to recombine the split.
Well, and the split is more important for strong scaling than for weak scaling.
Right.
So the balances are different if you use GPUs, because to saturate the GPU, you just need much more real space. And then you have more data in K space that you can parallelize over. If you do this with threads, you run, or initially only MPI. That was the reason to use threads, that we basically just have the MPI ranks on K space. And by using threads for parallelization, there's more data. So the K space doesn't have these tiny pencils to broadcast and do the transpose. Because the transposes are really killing you if you have next to no data, because everything needs to be turned around. It gets worse and worse the smaller the pencils get. And so with the GPUs, you have much more data, so you have more grid points. So it will hit you later.
Yeah.
But basically, numerically, it will always kill you at some point.
Yeah.
Because the distribution you can do for the K space is 2D, whereas for real space you have a 3D decomposition. So you're running out of space eventually.
Yeah. Just would be interesting how we hit that point on point 2 yet.
Okay. The other part of this is when you go to do the real space part on 7 GPUs or 6 GPUs. Basically gonna slow down that part by that fraction. So you're hoping that you're gonna increase that time, but you're hoping you get the P3M parts for free at the time, because it's being done at the same
Oh,
time.
I understand now.
So
Right.
whether that actually works or not, there's a lot of
I see.
trade-offs, but that's the best you can do. So,
Yeah. Just to bring that point about the parallelization home, so it's in the CPMD code, where it doesn't do pencils but only planes. So you get hit by this scaling out limitation much earlier. But what they effectively did is, for the regular code, once you run out, you just have processes idle in K-space. And then later, they parallelized over something else, like the state. So you need to, in DFT, you need to do a Fourier transform for every state.
Yep.
And then basically, you would do something that's equivalent to the multi-replica because you have the same system. And then you would have multiple replicas, and each would do a subset of the states where you need to do the projections from the wave function.
Yeah, but I still think that for the sake of the benchmark, not having hidden the nutrient time given by other computations, it's kind of, I mean, by design can be expected because you can see then how everything is done non-optimized super computer.
Yeah, no, I think you definitely want the numbers you've got to compare and see.
Yes.
Better, and
Yes.
just the fact that you didn't actually mention the size of the mesh for this huge problem, but I'm certain that's the biggest K-space or P3M and FFTs that's been done with LAMMPS. There's been some very big problems, but they're usually not charged.
Yeah.
Well, but you couldn't have done it because of the overflow.
Yeah, you were
But-
limited at some point. You
Yeah.
realized, okay, now
But there's
now
also,
it's prepared for more.
yeah, but there's also another parameter you can play around with. That's the extrapolation order.
Yeah.
That determines, so if you use a short order, you have to have more grid points, and so you also have a trade-off in whether you get faster outside the FFTs and then have more data to parallelize over versus being more efficient and then spend a bit more time on the applying of the forces of reading the grid
You
data.
can do the same thing if you put cutoff, with more of it in real space, and less in case.
How long we got that question before?
Was that?
We got the question before.
Okay, yeah, so that, I mean, those are, in principle, those don't affect the accuracy of the problem at all, but they adjust things and they might improve.
Yeah, and in those optimizations, let's say, so we are trying to push the limits of the machine.
Yeah.
So we would like to have the code to be optimized enough to be able to run. But then tweaking it so that you are doing less calculations, probably not the question. We have to push. We want to have the highest congestion of the network.
Because it's a benchmark.
No, I understand, but I'm just saying the two things that Axon I just mentioned, play with the stencil size and the actual real space cutoff size. Those are totally legitimate things to do. You're not affecting the principally, you're not affecting the accuracy at all. They're just like tuning parameters that on one machine versus another, it'd be better to do something versus the one versus the other.
Well, the problem with long-range Coulomb is you have two conditionally convergent sums, and you split them in a way, and where that you can get them better converged, and then where you do this switch over from one to the other depends on how efficient you compute each of the two sums. So in this case, if you're running at scale, you're running into the problem that you're spending more time on the reciprocal space sum than you spend on the real space sum. And by putting a bit more work in real space, you may gain performance because the real space kernel parallelizes extremely well on the GPUs, where the K-space restriction is mostly a restriction of MPI communication.
Yeah,
So if you limit the communication, you improve the performance. So that's when you would have support for single precision FFTs. You would also have at the scale limit a benefit because you're cutting the data you're sending around in half.
Though,
Now, just
like you showed it was about balanced at scale, right? It was like 50% case-based. I mean, isn't that about ideal?
Typically on the CPU, it's about 60% pair and 30% case-based, and then 10% the rest communication. That's roughly, in my experience, the optimum. On the GPUs, all bets are off because the acceleration is different for AR cases.
Yeah.
I don't know if it will really help or not. I'm just saying that's a parameter you can tune input and try it out.
So, Fernando, do you know about how long it took to run the benchmark? At
The
scale,
whole run.
like the,
Not very long.
Yeah,
I can provide information.
yeah, that was another question is for both
Yeah.
the reacts and
The
the bio
length of
problem. What's
the,
the time?
Yeah, do you have any-
First step.
seconds per step, or even just the atoms, the million or billion atom steps per second?
yeah, it is, well, actually, I wanted to put it in a table, but it is right here. This is the million
Okay.
atom step per second.
So that's like,
10⁵ to 100 billion.
do you have the, can you do the water one?
It's
Same thing.
it's the same.
So it's like, 4 e to the fifth valve? Oh, no, no, sorry, yeah, I was looking at the, yeah. Okay, so 10 to the fifth, million atom steps per second,
Uh-huh.
cool.
Well, that means, that's interesting, because that means reacts 20 times slower than this. Because reacts is pretty slow.
But there are differences.
It runs on
Different sizes of.
So one is the water, this one, and the other is the penta.
They're also different sizes.
And the size.
But again, a million atom steps per second normalizes.
It normalizes, yeah, so it doesn't matter if it's
So,
still.
yeah, I mean, the scaling of the K space is n log n, whereas, the QEQ, we don't know.
Reacts is not as slow compared to SBC as I'm used to seeing. So I don't think it's just.
So you're expecting to see to be reaccepted slower than the.
No.
The other
Reacts
way
is, well, Reacts FFF is certainly slower. I have to go look back and look at the tables, but I think on small problems, it's like maybe 20 times slower than SBC.
Yeah, well, what would be interesting to see would be the GPU utilization during those runs.
Yeah, because React runs really well on GPUs. Especially.
Very good point here.
So-
Okay, now diving into a little bit, I'm sorry.
Oh.
No, go ahead.
Well, so I'm just trying to calculate the time steps per second, so it's 466 billion atoms?
Yes, so
Okay.
if you go to the website, everything is there, but
Oh,
I
okay,
will have them in a table.
cool, okay.
So let's dive into the communication study, which was a MPI test to be able to understand a little bit more the communication patterns. So I have this here to refresh your mind in regards to the configuration of the two different clusters we were testing on. Importantly, we have to remember that you have in one side 4 GPUs with 8 graphics compute drives. Each one has 64 gigabytes of RAM for fronting. While in Summit, you have 6 NVIDIA GPUs with only 16 gigabytes. So that is already a constraint to be able to compare them. Because if you wanted to saturate the memory, we have to use different system sizes for each of them. And in the other hand, in Summit, you only have one network interface card that is attached to normally PCI Express. I mean, nothing new there. But as you already saw, we have 4 network cards and interfaces in the NICs per node in Frontier that are connected to the GPU, right? So that's very important for communication and for also to have into account the topology of the network. So we have a flat tree versus a dragonfly. Okay, so what is the status of this at scale? So you have communication patterns here. So basically Frontier spends something like 35% of the run in MPI computation, MPI communications. Meanwhile, it has a 65% in compute, branching numbers. On the other hand, Summit is spending 66% on MPI communications, not only MPI send is one of the biggest ones. And this is for the water, liquid water system. And only 34% compute. That is very important. So why do you think this is? Because of course, in Summit, you have only one way through the network. Using the NIC interface, meanwhile, you have in Frontier 4 outlets to be able to communicate to other nodes. That is very important.
Wait, I want to make sure I understand these parts. So quick, is this one of those two problems, React?
No, this is comparing the clusters. This is Summit, this is Frontier. And
Yeah, but it's
everything
the
for
SBCE example.
This is the
This is the
SPD
FCC one.
example, yes.
Okay,
So,
so you're running on Frontier a much bigger problem.
exactly, so here we have in Summit only 6.29 million atoms. Meanwhile, in Frontier, you're running 50 million.
So is that part of the reason that the compute percentage goes up?
So it is normalized to the size of the GPUs. Remember, in the GPUs in Summit, you have only 16 per GPU, 6 times.
Six.
Meanwhile, you have 64 gigabytes per GPU, 8 GPUs in Frontier. And so, of course, Frontier is because it has more data, injecting more data into the network, right? But it has a four-way connect to others, so it has 4 NICs.
Okay.
And on the other hand, you have Summit with all this memory communicating to only one interface.
I remember one thing I also learned from the IBM people on BlueJean. So once you go to thousands of nodes, latency becomes much more important than bandwidth. And the problem with the fat tree is if you have all-to-all communication with each level in the fat tree, you add to the latency.
Yeah, but this is only, that's why the other MPI is in orange here. But this one is referred only to MPI send, so there is no auto point-to-point. So that's why.
Yeah, but you still have the larger latencies.
You will have the larger latencies in there. Yes, that is also true. That is another way to explain it. So it has to be with the ratio of NICs per GPU and also the latency of the topology of the network.
So to me, this is very interesting data. I don't fully understand it, but I think I understand some of it. One thing that would be.
So maybe this one is gonna help you to understand.
Well, let me just say one more thing.
Yes.
If you could run the Summit size problem on the Frontier, so run that smaller problem on the same number of Frontier nodes, I'd be interested to see a third pie chart
Yes.
for how those compare.
But now here you will have, I guess, less data to inject to the network because it's gonna be a smaller size for Frontier.
Yeah.
So what I'm expecting without even doing it is that it's gonna be probably better than those numbers.
Well, but really you're just showing ratios. So whether the compute for the smaller problem can be relatively
Okay, so
faster
you're saying because the amount of computation is gonna be lower. So
Yeah, everything's gonna be faster when you do it, but I don't
That
know
would
if
be
the
interesting
ratios
to
are
see.
gonna
I
change.
agree.
I don't know.
Yeah.
Be fun to make predictions, though. That's always good to see. And
Then
then
we will see. It is.
Who got it right?
Yeah, I know.
don't
I
have any
agree.
idea.
I agree with you. Yes. So this is where it comes to play the what is in progress, the key space modified collective yes. So instead of using the point-to-point communications, which I guess is I receive and MPI send for that case, you can see the difference. We put this, I think it's the other way around. So let's start looking at this one, Summit. And you have to be aware that this one is time step per second as well. And you have to be aware that they are not in the same scale, unfortunately. This is 100, this is 10, but actually everything is between 0.10 and 1 here. So that will be in this part right here. So in the end, at full scale, the biggest number of nodes, the time step per second is kind of similar, right? For the point-to-point large, so the large one. For the small one, if you see, what you take from here, from Summit, is that it is really efficient in one node compared to Frontier. It's absolutely amazing. But once you go outside of the node, you start to see how it rapidly decreases the performance when you're using the send, I receive. And when you start using the collectives, you see a much better performance, like it's shown here in the orange line. For the blue line here, it's incomplete because there is a bug. We are already not certain. I think it's a hardware issue in Summit right now. Summit is falling apart. We're not being able to calculate the larger points here, but you can see that the trend is gonna be that it's also gonna improve the behavior of the space if you use the collectives instead of the point-to-point. But in Frontier, the story is totally different. As you can see, the point-to-point communications in Frontier are absolutely amazing. Actually, they are very optimized. Remember, Frontier is a crane machine, an HPE crane machine, so it has MPitch crane, a crane MPitch, which is highly optimized for point-to-point communication. But you can see probably that the collectives in that MPI implementation, they are not very well optimized. You can tell that basically that using the collectives at any point, more or less, they start the same, but they degrade very quickly, right? So we have to see whether we can send this information out to the vendor, they can optimize the algorithm they had implemented for the all-to-all algorithm, but in general, you can see that all-to-all depends on the implementation, depends on the network performance and the network topology as well. Even though we're expecting that that one will perform better in the Dragonfly than the factory, but fortunately, as of today, it's not working. But still, we think this is an important improvement if for your computer architecture, the point-to-point is a bottleneck. So you can try the whole.
So what is in the left plot there? What is small versus large? Collective small, collective large.
I think it's the buffer size, the amount of data.
So is that a setting or?
Yeah, it's a setting in the MP with MPI. Set buffers
Okay, so,
for MP.
okay, so to be running at that right edge, but you can run with either collective small or collective.
Right. Yes.
And it's the same setting for point-to-point communication.
Are you sure that's not a problem size?
Or maybe.
Well, he's running it for all the problems. It's both for all the problems.
No, this is the number.
Like a strong, he's like strong steam,
This is strong scale.
so he has a big and a small. Number of atoms.
Weeks. Right. He's running a huge problem.
Oh, is this,
This is the bench.
No, this is different. So remember, this one is using only this case.
Right, but this is SPCE.
Yes,
okay,
Water.
but-
Yes.
so
Big
it's-
FFT, that's what we're looking at on the left.
Yes.
So, when you say implement case-based modified collective, so that's in the code. And are you saying something needs to happen in LAMMPS for that to be able to do the MPIL, invoke the MPIL?
I think it's already in the
Yeah, so it wasn't ported to Cocos and Nick ported to Cocos and then he optimized it further.
What do you mean optimal?
He
It's just
Basically,
making an MPI call.
refactored. Well, it's like the setup and all that was
Oh, that's
expensive.
in the LAMP side, to set up the
Yeah.
buffers for the MPIL call. So
Yeah.
that was already done.
By Paul Kaufman for the CPU version.
There was 4
Also, but it wasn't that case-based modify option not recognized by Cocos switches.
Yeah.
Okay, but now it is because they can run it on Summit
Yes.
or Frontier. But
Uh-huh.
you're saying, the other thing you said, Fernando, is the actual MPI all-to-all, so that's not LAMMPS, it's within the MPI library.
Yeah.
May
It's
not
not
be that great on.
Yes. That might be one of the reasons. There are too many variables, but we think that that is one of the reasons.
Okay,
But still, even though it doesn't work well for Frontier, showing up the case of Summit makes the case to, well, if you have in your system, in your setup, in your implementation of the MPI, the bottleneck is point-to-point communication.
Yeah.
Then you can use the strategy.
Yeah.
We should actually run it on our local machine here, which also has InfiniBand, to show whether the InfiniBand
Is the one.
benefits, and that would be something that would apply to a lot of users.
Okay. Very good then, you know. Okay, so these are takeaways. So basically, I already explained this. The IPMI, the MPI send is the bottleneck in your machine, so you should consider it objectives instead. And actually, like we do, I mean, Frontier has different racks NICs per GPU that might actually active factor as well. When, for example, you use the point-to-point, it's going to be kind of improved for that reason, but in any case, it's not the case for every cluster. So if we think of different machines as in general, I think they all share just one NIC per compute to the fabric. Specifically, if it's InfiniBand, I'm pretty sure it's just one. And so that would be beneficial for many users.
Well, then,
So,
yeah, I don't know what the next machine will be a
well,
six.
who knows?
Who knows? But maybe this will come out.
Yes, who knows? So maybe it's just one, so I would think that. Okay, so the next step. So basically, in the time frame or macro we have ahead, so there is this continuous study, the current P-train communication pattern in new HPC architecture. So we really did the study for Frontier and Summit, so I'm expecting to do it for new architectures. Something's coming up. No idea what that is. And then there are some algorithmic optimizations that they were done in the Cocos implementations that they should report it to the non-Cocos part as well. So I think Nick was only working primarily in the Cocos part. But he's saying to onboard also these optimizations to non-Cocos part of the code. There is another, let's say, idea that hasn't been implemented. Is probably do a kind of optimization of the point-to-points. So instead of using an MPI send, probably creating a buffer, so you can use MPI I send instead. So that would be helpful as well, specifically in systems where they have enough memory to hold the buffer. What do you think about that? Actually, yeah.
So I think it's something worth trying. There's another variant there, which I mentioned briefly in my talk a couple of days ago, which is between posting the receives and doing the sends. If you put a barrier in there, then you can do R sends because you know it's a ready send, because you know that the receive has been posted. The barrier ensures on the other processor it's been
So
posted.
you schedule all of them, then wait all.
Well, then you could still use the same buffer, but you could just shoot them out immediately. There would be no potential blocking.
So I know Nix has a lot of faith in this. So
Yeah.
we'll see how it goes. I'm actually curious to see how it goes. So there is something that actually is happening. Challenges, as anything, I think is more than a craft than a science thing. So you have to find the right incantation of settings. Literally, you have to find, you have to study your architecture. You have to find the right settings for your system. You already mentioned other optimizations that can be done, so that's important as well in our toolbox of settings to optimize. I think it's important to get in touch with the developers and community in general to get things done faster. So we thank you for your support and collaboration. And we look forward to keep working with you in optimizing the code for its scale. And if you have an unstable molecular dynamic system at scale, it is hard to know whether it's one thing or the other. You just have to try to ask around and play with the code. And yeah, I mean, you can give up or you can actually ask for help. This is what we do. Fortunately, I have access, so you can keep helping out with this. So lesson learned. So just keep in mind, you have to keep your atoms relative to the int max, specifically for the replicate command we already discussed. There will be some small overheads that can be addressed. So consider using SBcast when you can, while you can, in any any system in any cluster that has SLARM and thus has this option enabled. Remember that systems are liable to latency, not capacity. So this is already we talked. So depends on the topology, the network that you have. So if you already have 1,000 atoms per second and it's slow, it will be slower. It doesn't matter what you do because it's related to the nature of your system. And for example, in Frontier, if you have 12 gigabytes memory per node, it can actually fit 50 million of atoms. So it depends a lot of in your computer, more or less. This is the message. And then you have to learn about the communication pattern and to be able to track it down if you are able to optimize it. And that's it. So recap, this is everything we've done. You can find the OFC 6 event benchmarks in that address. So I encourage you to go there. There is a package. It's not the only one. So you can find different applications there. LAMMPS is just one of them. Others too. But if you go to the LAMMPS part, you will find the description of each of the systems. You will find as well what are the validation settings. You will find the input files, the scripts to validate, to run, and actually the output files as well. So you can start playing with the numbers right away. You don't have to calculate them. You don't need access to the machine. They are already there. So that is helpful. For example, another takeaway is that using collectives instead of point-to-point communication might be an effective way to improve your calculations, specifically if you have a very good MPI implementation. So non-accurate one, non-accurate one, I want to say. No, accurate is very good, but not good. Also, and also, no, I mean, I've repeated this so many times, but I think it's very important for any user. You should know your system's architecture, and you should contact your people, the supporting people, to ask them how can you take advantage of that architecture properly. You can reach out to the developers or other users, to ourselves. In the benchmark website, you can find an email where you can contact us, and we will be happy to do so. That's all for me. Thank you very much.
It's all very interesting data. I've not seen any of this before. So Stan had mentioned you guys were doing cool things, but this was very illuminating. But I just want to make one follow-up on that second bullet about collective versus.
Yes.
So everything, as I understood it within your talk, this question was being zoomed in on, but it's specifically for FFT
Yes.
communication.
Key
So-
space mode.
So point to point is used for other things in LAMMPS and lots of other codes, but this trade-off and try to assess whether collectively point to point is what gets. Point to point is a really broad thing in MPI, but the point to point that's done in FFTs is more like, kind of like an all-to-all, or as you call it, many-to-many is a better thing. And so all these trade-offs between them are really kind of specific, I think, to FFT. Other places you definitely point to point. So,
Because, you know,
no, I wouldn't make that
50%
second
or
bullet
more
point
of the
too
time,
broadly. I
right,
guess.
50% or more of the time of the computation is spent in case.
Yeah,
It's
in this
worth looking at,
particular
yes.
problem, yeah.
It'd be interesting to look at hack too, and then they do some really big FFTs.
And the cosmology,
Yeah.
particle based code, they do big.
What is the name?
HACC.
The other thing which you might want to do is talk, and these people are at Oak Ridge, connected to Oak Ridge, it's the Hefty people, that's another FFT library, and LAMMPS has support for that. Their library, and again, I don't know how well integrated it is with Cocos.
Not
But-
a, yeah, it won't run on GPUs.
Hefty,
Yeah.
well, the Hefty itself does, but maybe our
Yeah,
our
our-
bundling
well,
of Hefty does not.
Yeah, okay, so it's not integrated with code.
So, okay, that's something to do, but they would be interested to know and make it, how their Hefty would, how their FFTs would
We
perform
handle
in this problem.
this size.
And maybe They might have to work with Stan if they want to do it through LAMMPS, but maybe they might be able to run exactly that size FFT. I guess they couldn't run P3M unless it was LAMMPS, but they might be able to give you some ideas about these FFT issues as well.
Yeah, I think at some point benchmarks results as we are improving to the codes we improve are going to be updated. So they are going to be pushing more toward.
Just one more historic remark on optimizations that were done for blue gene machines. So the blue gene was special in that way that it actually had a tree network and a torus network. So you could choose which of the two were used for which kind of MPI calls. And that made quite a bit of a difference for these collective optimizations, because it would just utilize the most effective network for the task at hand. That's one of the things that make the blue gene special.
Yeah,
Also
I think
very
the other
expensive.
thing that made it special, and for some definitions of special, is that it's a pure CPU machine. It had extremely slow processors, but it had a ton of. So the MPI communication that they worked so hard at was actually very fast compared to speed, which they needed because you could run 1 million MPI tests or something like that. So machine like these now, or Summit, is super fast compute and relatively slower MPI compared to that. So you're kind of working at the opposite end of the spectrum on a blue GQ machine versus
Because you have so many
GPU based machine.
latency. Quality is not. The Dragonfly was choosing things that cost quality there. And of course those tools. Because it's huge.
Yep.
Instead of starting a factory for that monster, very expensive one, very powerful. Yeah, so there is a trade-off.
But you're running this with 8 MPI tasks per node. You use each
So
of the
we
GPUs?
have, yes, this is for one
Yeah,
GPU.
so you're almost using 100,000 MPI. That's pretty big.
Pretty big machine.
It's a big machine.
Yeah.
Okay, thank you.